In this section, we're going to talk about solution concentration specifically. We've already talked about it qualitatively being concentrated or dilute, saturated, supersaturated, and unsaturated, but now we're actually going to give specific measurements. So the ones we're going to talk about are mass percentage, parts per million, and parts per billion. And these three are actually very similar, which is why they're the same color. And then we have these three, which are kind of similar, which is mole fraction, molarity, which we've already done, and another term called molality, not to be confused with molarity. So let's jump in. Starting off with mass percent, it is just like a normal percent. We're going to take if we're talking about a certain component, we're going to take the mass of that component in the solution, divide by the total mass, and multiply by 100. Since it's a percent, it's going to be between 0 and 100, and so that's a way to keep your numbers in check. So starting with this first problem, we make a solution by dissolving 13.5 grams of glucose in 0.1 kilograms of water. What is the mass percentage of the solute in the solution? So we look at 13 grams versus 0.1 kilograms just to get those on the same units. So we are comparing apples to apples. We're going to take 0.1 kilograms and get it into grams. So there are 1,000 grams in 1 kilogram, making this amount, 0.1 times 1,000 is 100 grams. So we're comparing 13.5 to 100. So since 13.5 is less, and we know glucose is the solute, so we're going to do percent glucose is going to be the mass of glucose divided by the total, which is the mass of glucose plus the mass of water times by 100. Oftentimes what people will do is they'll just divide by the solvent, and you actually want the total mass though on the denominator. So we'll do 13.5 grams divided by 100 grams plus 13.5 grams times by 100. So our denominator is going to be 113.5. So then we can divide those and multiply by 100, and we get 11.9% glucose. The next problem, we're finding the mass percent of sodium chloride in a solution that has 1.5 grams of sodium chloride and 50 grams of water. So we're going to do percent of NaCl is going to be the mass of NaCl divided by the mass of NaCl plus the mass of water times 100. So we're going to do 1.5 grams of sodium chloride plus 1.5 grams of sodium chloride plus 50 grams of water times by 100. The denominator is going to be 51.5. So we'll do 1.5 divided by 51.5 times 100, and we get 91% sodium chloride. Now parts per million and parts per billion are very similar. So percent means per cent is 100, so per 100. When we're talking about per million, parts per million, we're going to multiply by a million instead of by 100 like we did in percent. And if we're dealing with a billion, we're going to multiply by a billion. So the parts per million of a certain component is going to be the mass of that component divided by the total mass of the solution times by a million, or 10 to the 6. So if I have 2.5 gram sample of groundwater was found to contain 5.4 micrograms of zinc. This micro means 10 to the negative 6. So it wants to know the concentration of zinc ions in parts per million. So we're going to find the parts per million of zinc, and that's going to be the mass of a zinc ion divided by the mass of the solution times by a million. Now notice it says 2.5 grams of the sample of groundwater. This is not just pure water, this is the solution. So that is the solution mass. So we don't need to do some adding on the denominator. But we do need to keep the units similar. So I'm going to convert 5.4 micrograms into grams. So we're going to do, there are 1,000,000 micrograms per gram. You could also do 5.4 micrograms, and you can say that there are 10 to the negative 6 grams in 1 microgram. Either of those works for the conversion. That's going to give you 5.4 times 10 to the negative 6 grams. So that's what we're going to put up top, divided by the total solution, which is 2.5 grams of groundwater, and times by 1,000,000, 10 to the 6. So we do that math. Actually, what's interesting is this 10 to the 6 and this, or 10 to the negative 6 and 10 to the 6 are going to cancel out. And then we end up getting 2.16 parts per million of zinc ion is how you would record it. Now, mole fraction is also very similar, but now we're starting to get into moles, and so it's a good segue into the other units. But mole fraction is the ratio of moles in a substance to the total number of moles in the solution. So once again, we have moles of the component divided by total moles of everything. But instead of multiplying by 1,000,000 or 100 or anything, we're just not going to multiply. So it's going to be ranging from 0, a mole fraction of 0, to a mole fraction of 1. 0 being if there was no solute or none of that component, and 1 being if there was only that component. So somewhere in the middle. And then also mole fraction is unitless, so we won't write any units for it. The variable for mole fraction is this symbol chi. It's kind of like a fancy X, just FYI. So an aqueous solution of hydrochloric acid contains 36% hydrogen chloride by mass. Calculate the mole fraction of HCl in the solution. So how you want to approach these types of problems with this mass percent here is say that you have 100 grams total. Then what you're able to do is say, if I have 36% HCl, then if I had 100 grams, I'd have 36 grams of HCl. Now I would have a total of 100 grams of my whole solution, but since mole fraction is, we're going to have mole fraction of HCl is going to be the moles of HCl divided by the total moles, which will be the moles of HCl plus the moles of water. So we need to not only get the moles of HCl, but also the moles of water. So if I had 100 grams total of my solution, 36 was hydrogen chloride, then that means 64 grams would be from water to make the total 100. So we're going to divide by the molar mass, which is 36.45 grams per mole for hydrogen chloride and 18 grams per mole for water. You end up getting 0.988 moles of HCl, and for water we end up getting 3.55 moles of water. So we're going to plug it in, 0.988 moles divided by, I just go straight down, 0.988 moles plus 3.55. We're not going to multiply by any number, and we're just going to plug that on in. We end up getting 0.218 for my mole fraction of HCl. So it's a number between 1 and 0, and so that's a good check for our value. The last thing we're going to learn about is molarity and molality. Now these are very similar, and they are actually, their shorthand is either capital M for molarity and lowercase m for molality. So if you're a person who likes to write lowercase for everything or uppercase for everything, you cannot do that right now. That really is specific, and so uppercase for molarity. As a reminder, molarity is moles of solute over the total liters of solution. So that's the total volume of whatever the solute or solvent is in the solution. Molality, on the other hand, is lowercase m, and it is the moles of the solute, so it starts out the same, But instead of being the liters of the total solution, it's kilograms of solvent. So we have solute up top, solvent on bottom. And again, shorthand, little m, moles per kilogram. Just like I could say like I have a 2.5 molar solution, and that molar means I have 2.5 moles per liter. I could say I have a 2.5 molal solution, lowercase m, and that means I have 2.5 moles per kilogram of my solvent. So we can use that lowercase or uppercase m as kind of a shorthand for a combo unit. Now, why would we have two different things? Well, really, we're usually dealing with water as our solvent, and when we have a dilute solution, then the molarity and the molality are similar. And that is because the density of water is 1 gram per milliliter, and so we can go between kilograms and liters easily when they're dilute because the solution will have a density close to 1. When we are going to do certain properties that involve varying the temperature, we would want to use molality. That's because when I'm dealing with a liquid and I get it really hot, then it's going to actually expand as those molecules are moving faster. And when I cool it down, it's actually going to contract as the molecules are slowing down. But if I'm wanting to know concentration and I want to vary the temperature, I don't want to use something where the volume is going to be changing. So I want to use molality because molality has mass of my solvent, and that's not going to change with temperature. Mass stays the same. But molarity does vary with temperature because the volume changes. And so in the case where it doesn't really matter, we're not dealing with a lot of temperature changes, then molarity is just fine. If we want to convert between molality and molarity, we're going to need the density of the whole solution. And so that would have to be given to you. So let's practice how this works. This problem wants us to calculate the molality of the solution made by dissolving 36.5 grams of naphthalene, which is C10H8, in 425 grams of toluene. So we can see immediately that the naphthalene is the solute because there's less of it. So we're going to say, okay, molality equals moles of our solute, which is naphthalene, C10H8, divided by kilograms of solvent, which is toluene, C7H8. So what I'm going to do is I'm going to say I have 36.5 grams of C10H8, and right below it I'm going to write 425 grams of toluene. So for naphthalene, I want to get into moles, so I'm going to use the molar mass of naphthalene. It's actually 128.063 grams per mole, giving our amount of moles being 0.285 moles. So that's what's going to go on top. And then on bottom, we want to get our solvent into kilograms. So I am in 425 grams, so I'm going to say there are 1,000 grams per kilogram, making this 0.425 kilograms, and that's my denominator. Honestly, for a lot of these problems, I'm going to usually write down the amount of solvent and solute, and I'm going to usually do some kind of conversion with them. So we're going to plug that on in, and we end up getting that our molality is 0.671, and we can write moles per kilogram, or I could just write lowercase m. All right, a density problem. A solution with a density of 0.876, so the density of the solution is 0.876 grams per milliliter, contains 5 grams of toluene and 225 grams of benzene. So now toluene is actually our solute. Okay, so 5 grams of C7H8, and we have 225 grams of benzene, which is C6H6. Calculate the molarity of the solution. So we know that molarity, capital M, is moles per liter. Moles of solute, which is going to be C7H8. And we want the total volume of the solution. So let's start with the moles of toluene. We can calculate the molar mass. This is 92.063 grams per mole. And that's going to equal 0.0543 moles. So that's what's going to go in my numerator. And then for the denominator, now this is the volume of the solution. So I'm actually going to need to take the total mass of my solution, which is my solute, plus my solvent. So I have actually 230 grams of my solution. And it told me that my density was 0.876 grams per milliliter. So you're going to actually take that density and get into milliliters, 0.876 grams per milliliter. And we want it to go into liters, so I can convert 1,000 milliliters per liter. So that ends up giving us a solution volume of 0.2626 liters, and that will be in the denominator. So we just will say the molarity is, we divide those two numbers, 0.207 molar